Okay, so I need to post like an addendum to the video that I made for IOMk and DIOMk. And it's the following. So remember that we are looking at solving systems like AM. We're looking at doing xm plus x naught plus vm times ym, and ym is equal to hm inverse times beta e1. In other words, ym here is the solution to hm ym equals beta e1. Okay, but where does this equation come from? So if you think back to when we, several weeks ago when we were first deriving these methods, maybe week 7 or week 6, we saw that what we really want to solve is Vm transpose A Vm Ym is equal to beta E1. But then we saw in the full Arnoldi algorithm, this right here is equal to Hm. Now where does this identity come from? Well, this identity comes from this identity right here. If you take that identity and multiply both sides by Vm transpose, you basically get this identity here. There's another little part of the argument that you need to make, but that's essentially where it comes from. This identity right here, as I mentioned, is simply true by the way that we're constructing things. So this identity is true in IOMk. But in order to go from this identity to this identity by multiplying both sides by Vm transpose, you need to have that the Vm matrix is orthogonal. That's true in FOM, but it's not true in IOMk. So in other words, I need to explain to you why solving this system is equivalent to solving this system in some sense, even in the incomplete orthogonalization method. And that is what I should have done in the previous video, and that I am going to do in this video now. Okay, so first of all, maybe let me remind you that V1, how do we make V1? I don't even have it here in the main loop, but it's just equal to the residual R0 divided by the magnitude of R0. But the magnitude of R0 is just beta. So V1 is equal to the 0 residual divided by beta, or we could say R0 is equal to beta V1. Okay, so now what we need to show is we need to show that the mth residual is going to be equal to a multiple of the vector Vm plus 1. That is a thing that's going to make this computation make sense. Okay, so we're going to compute Rm. Rm is equal to B minus AXM. Okay, so what is xm equal to? So this is going to be B minus A x naught plus Vm Ym. And then doing computations as we have done before, B minus AX naught is equal to R naught. So this is equal to R naught minus A Vm Ym. And remember, R naught is equal to beta V1. So we can write this as beta V1 minus A Vm Ym. Okay, so now what can we do here? Well, this identity is still true. This identity is true just by the way that we're constructing things here. So we can write this as beta V1 AVM is equal to Vm plus 1. And actually, I forgot the bar there. So AVM is equal to Vm plus 1 Hm bar. So this is going to be Vm plus 1 Hm bar Ym, like this. But now, hold on, let me make sure I have this right. Okay, so notice that the first entry of Vm plus 1, or the first column of Vm plus 1 is simply V1. So Vm plus 1 times E1 is equal to V1. So I can basically factor out a Vm plus 1 and get Vm plus 1 times beta E1 minus Hm bar Ym. Okay, so I'm gonna erase everything and copy this up here. Okay, so we've got Rm is equal to V m plus 1 times beta E1 minus Hm bar Ym. Okay, so now what's happening here? So Hm bar has m columns but m plus 1 rows. So what we want to do is we want to choose, and remember the top part of Hm bar is just Hm. So choose Ym such that Hm Ym is equal to beta E1. So in other words, choose Ym so that Ym is a solution to this equation. That is a thing that we got to one way in the FOM method, and we're getting it to another way in this method here. Choose choose Ym so that Ym is equal to beta E1. So then carrying down my computation for Rm, I'm going to have Rm is equal to Vm plus 1. Now what's going to happen over here? If Hm is equal to beta E1, it means that the first, this is an this is an m plus 1 dimensional vector. And the first m entries are just given by beta E1. And we have beta E1 here. And so what we're going to be left with is going to be a matrix or a vector with almost all zeros. And the last entry is simply going to be the dot product of the last row of Hm bar with Ym. Well, what is the last row of Hm bar? Remember, it's all zeros followed by Hm plus 1 m. Okay, so the last row of Hm bar is all zeros with one, the last entry is non-zero. So then when I do the dot product of that with Ym, I'm just going to get the bottom right entry of Hm bar, which is Hm plus 1 m, times the last entry of Ym, which I'm going to call Ym m. Okay, sorry, I'm going to have to erase this. But now when I do Vm plus 1 times this vector, it's just going to be this scalar right here times the last column of Vm plus 1. And so now the last column of Vm plus 1 is the vector Vm plus 1. And so we're going to get minus Hm plus 1 m times the last entry of Ym, which we can write as Em transpose Ym, and then times the vector Vm plus 1. And this is the identity that we need to have the residual in this formula right here. This is the identity that we need for this projection to make sense. And it's all because, well, it's in, if Hm is equal to beta 1, then we get this formula for the residual right here, which is the thing that we need for the analysis of the IOM algorithm to work. Or it's the thing that we needed for the analysis of the FOM algorithm to work. And so that same analysis we can just sort of plug in with this as the residual. Okay, so I needed to say that in the previous video because I mentioned that the easier version of the identity is not true in this case because it requires orthogonality, but then I never explained why we were still using it anyway.